pleasure of having with us Inês Ochoa. She will talk about searches for new physics in Atlas. Inês studies physics at the University of Coimbra. She did her master's degree within the LAP group at Coimbra. Afterwards, she did her PhD studies at University College London, where she worked on Higgs boson searches in Atlas. Her postdoc was done at Columbia University. She worked mainly on the electronics for the upgrade of the liquid argon calorimeter in Atlas and searches for new physics as well in Atlas. And today she is a La Caixa Fellow, LAP Lisbon, working again in searches for new physics in Atlas, which is the topic of the seminar today. So please, Inês, whenever you're ready.
Okay, thank you very much. And hello, everyone. Thank you for having me today. So just to confirm, you can hear me okay? Is the volume fine? All right. So, okay, so I'll be talking about today about the hunt for new physics, specifically for new particles with diboson final states at the LHC and with the Atlas experiment. Okay, so here's the sort of the outline of the talk. I want to start by motivating the search for new physics and specifically the role of diboson resonances or diboson final states and where they are most relevant. And I'll then give an overview of a selection of a few of the latest Atlas results, a couple of them only very recently published or made public, and just a couple of months ago. And I'll focus specifically on a class of analysis, which we call the fully hadronic final states, and I'll explain why. And then a few of challenges associated with those analyses. But then I'll mention what is next for the LHC, so where we are in the LHC timeline, to give some wider context and on what the experiments are focusing on and when we expect more data. Then I'll talk a bit about what comes next, right? So given that timeline, what can we do to improve our searches, also to broaden their scope and make sure we're not missing out on any new physics if it's there in the LHC dataset. Okay, so starting with the motivation. So we have to start with the Senna model, of course, and the Senna model, despite its successes and with the discovery of the Higgs boson back in 2012, it's obviously an incomplete picture of the universe. So one thing, for example, it doesn't account for is dark matter. So there's no particle explanation for dark matter. There's also a few things that make people a bit uncomfortable, maybe not necessarily indicating something is missing, but certainly something that we'd like to be able to explain. For example, the matter dominance over antimatter, and given the mechanisms that we know of in the Senna model, and also no apparent structure for the distribution of masses of particles or number of generations, and of course we can't fit in gravity either within the quantum field theory framework. So, all in all, it's a pretty, I would say, very successful in many ways, but also unsatisfactory picture, and due to different reasons, right? So. It can't be the whole story, and so we do believe it needs to be extended in some ways, but how, right? So that's the question. How do we extend the Senna model? And fortunately or unfortunately, depending on how comfortable you are with the uncertainty, there are many possible ways to extend the Senna model, and there are different scenarios that try to address different things, like the missing dark matter candidates. But I would say no really single well-motivated scenario. So this is, in my experience, at least in my view, a very sharp difference from the perspective that I guess we had a few years ago when in Atlas, at least, I felt like people were very focused on either the Higgs, looking for the Higgs, or perhaps SUSY, which was a favorite of many people. But I think now things are very much less single-tracked. I would define it that way. So at this stage, there is, I would say, a need for an unbiased and comprehensive approach for the searches to new physics that really make use of the LHC dataset. And so the good news, of course, is that we do have a very vast and rich dataset of the 13 TeV proton-proton collisions collected by the LHC. So thanks to a very successful LHC Run 2 after the LHC Run 1. So I won't really introduce the LHC exactly here. I'll just highlight a couple of things on this slide. So first, this plot on the left shows how well the instantaneous luminosity, or in other words, the collision rate, increase over the years of the Run 2 data set. So especially highlighting the 2017 and 2018 data collection, where the records were broken in terms of instantaneous luminosity. And secondly, on the right, I just want to highlight this plot, which is not new, but I always like to show it. It's one of my favorites. It shows the LHC BIM orbit in terms of the relative energy change in the y-axis as a function of time, and that's during the New Zealand earthquake. So we can see that it's very visible the impact that it had on the sort of the alignment of the machine. So you have to remember this is a 27 kilometer long ring, so pretty susceptible. Okay, so this is just to highlight how precise of a machine it is and how well it's been going, I would say. Okay, so there is no direct evidence of new physics in colliders yet, right? So when we've been, since the discovery of the Higgs, and also already before, carefully doing measurements of top Higgs and standard model processes, which so far have been in excellent agreement with predictions. And so still we know, or we hope it has to break down at some point within the LHC reach. One way to look for a breaking point, and perhaps the most direct and model independent way, would be to find a new particle, right? A new resonance. That would be, I'd say, the most dramatic sign of new physics at the LHC that we could hope for. And so here, what I'll argue for is the role of diboson final states in this quest. So of course, as part of a comprehensive search program that I'll highlight later as well. So the reason that diboson final states should be searched for then is put simply because there are many extensions in the Senna model that predict new resonances new particles that will couple to Senna model gauge bosons into the Higgs boson. And so the exact phenomenology will depend on the scenario itself. So it's not, from my perspective, point of view as an experimentalist, I won't highlight individual scenarios exactly, but I'll give a few quick examples in the next slide. But one thing that we can say, at least for many of these, is that they would address, or at least alleviate, the naturalness problem of the Higgs boson, right? So so this is the fact that the Higgs mass is very susceptible to the quadratic divergences, and it requires basically a fine-tuned cancellation between the bare mass and the radiative corrections. And so I guess there are different opinions here on whether this is in itself a good motivation, or should be a sole motivation for physics at the LHC scale, but it's at least a strategy that has been useful in the past in high energy physics. And so from the experimental perspective, also I can say that Higgs and gauge bosons have well-defined signatures that I'll talk about that can be targeted using state-of-the-art techniques, and they're very useful, basically very handy to suppress background. So they're a great signature for looking for new physics in that sense. So okay, so I would say, again, this is an important, I think, contribution to a comprehensive approach to searches in other final states as well. So I'll try and put that in context as well afterwards. Okay, so having said that, we're talking about diboson resonances, so a new particle or particles, X, I'll call in the next few slides, that can be gravitons or radions or new vector bosons or new scalars being produced at the LHC via different final initial states. So some of them highlighted here. So quark, anti-quark, gluon-gluon fusion, and vector boson fusion. Then through some coupling structure, we look for cases where these new particles will then decay through to a pair of gauge bosons or vector or Higgs bosons. And so through some combination, so you can see several combinations here highlighted in these Feynman diagrams, specifically those that are sort of more experimentally accessible. So WZ, Higgs, and photons. So these are all initial states, I should say, that we get at the LHC. And this plot on the right, I just want to highlight basically how we gained from the increased center of mass energy. So as you know, we're going from 8 TeV to 13 TeV for Run 2, which has the effect, due to the structure of the proton PDFs, to really increase luminosity, the effective luminosity of these initial states, and especially to give access then to the high mass region. That is the one that I'll be focusing on. So this sort of TV region here. Okay, so I said I mentioned many Stena model extensions, and I said I don't want to specify too much, so I'll just give a few examples. It's a very vast space, multidimensional space of phenomenology. So we often make use of simplified models to make generic predictions on specific processes. So for example, we try to formulate the problem in terms of just the mass of the new particle and its couplings to the initial state or final state particles. So in any case, just to give a few examples, these can be new scalar resonances, which show up often in 2 Higgs or more 2 Higgs doublet models. They can be new gauge bosons, so new W prime and Z prime. There's heavier versions of the W and Z boson from new gauge groups or some sort of more complicated structure. And they can be also spin 2 gravitons, for example, that show up in models with more extra dimensions that try to explain the weakness of gravity. Okay, so these will show up sometimes in some of the plots in terms of sort of as benchmarks to which to compare to. Okay, so let's talk then about diboson resonances, I'd say from the more experimental side. So depending on the final state that we're targeting, we are considering combinations of Ws or Zs or Higgs bosons as well as photons in some cases. So there are several combinations possible. Then of course, the Higgs and the W and Z bosons will themselves decay, so that their products is what we're measuring in the Atlas detector. So we can basically design different analyses that are optimized to target different final states, different combinations of final states. So either the leptonic decays of the Ws and Zs or the hadronic decays of the W and Zs. And for the Higgs, what's most common is that we just focus on the Higgs decay to a couple of B quarks, so BB bar pair. You can see the branching ratios there. So it's basically, that's the most often, that's the largely most dominant decay channel of the Higgs boson. So that's the one that we'll mostly cover. Of course, there's a trade-off, right, between how easy it is to reconstruct a leptonic final state because they're much cleaner than the hadronic final states, but the hadronic final states have a much larger branching ratio, and we can really make use of that in terms of statistics, especially when you're looking in the very high mass region, which I'll show. Okay, so I'll focus mostly on these fully hadronic final states, and I'll explain where, why, and where they're the most powerful. So something like the combination of what's shown here on the left. But okay, but before doing that, I'll just make a brief aside, basically to talk about jets. I think most people know what I mean when I say jets, but I just want to sort of give just the 2 main aspects that we care about in jets when we're talking about hadronic decays of Ws and Z bosons and Higgs as well. So okay, so jets are basically a collection of particles produced by outgoing quarks or gluons that get produced in the LHC collisions, including those that come from the W boson decay. So in practice, they're built, well, there are different types of jets in Atlas. The ones that I'll be talking about are built from a combination of charged particles, tracks, measuring the inner detector, and calorimeter deposits, both in the electromagnetic and hadronic calorimeters. So there are many jet algorithms, and it's important to pick the correct one for the physics purpose, right? So without getting into too much details here, what we want from jets when we're trying to capture W, Zs, and Higgs is 2 main things. So if you think as jets as sort of cylinders that are centered around the decay products of the boson, you have to use a radius of the jet that is large enough to capture and encapsulate the full decay products of the boson decays. And when you do that, because you're using a large radius, you're also very susceptible to pileup. So remember, in Atlas or the LHC, we had an average 33 collisions per bunch crossing in run 2. So we have, it's much more than what's actually illustrated in this picture. So it's very important to correct for that. And we also have the underlying event contribution from the proton. So which means that there's a lot going on in the detector, and you have to sort of subtract out especially from the calorimeters, that contribution from the pileup collisions. And so we do this via what we call some grooming algorithms that sort of clean up the large radius jet that you just use to reconstruct the W and the Z in the Higgs. Okay, so diboson resonances can cover a wide kinematic range. So we're talking about searching for new particles with masses of the order of 100 GeV all the way up to several TeV. So these, again, these show up in all sorts of extensions of the standard model. So we're really looking everywhere. Now at low masses, the leptonic decays are of the W and Z bosons are the most sensitive ones. So that's usually what you use for that region. Because it's easier to trigger. You also have a cleaner event reconstruction, even if you, in some cases, have a neutrino. On the other hand, if you want to reach the opposite end of the spectrum, as you push to higher masses, that's when you really enter the realm of the fully hadronic decays, which are ideally suited for this high mass region. So TeV region, basically. So first you get the statistics advantage because you get much larger branching ratios for the W and Z bosons decaying to quarks. But also you get, basically as you get higher and higher, you're moving away from most of the standard model background. So they'll just decrease. You get to a point where even in a fully hadronic machine, you're able to control the typically overwhelming QCD background. So I'll mention QCD background a lot in the slides. I just mean the quark and gluon initiated jets. So that's what we're targeting, basically this 1 TeV mass range. It doesn't mean we can go lower, but you usually run into problems of how to trigger those events. And then it's just also a combinatorial problem if there's a lot of jets and it's hard to control the backgrounds. Okay, so that's what we call then, well, first in this high mass regime, high mass of the parent particle means large momentum of the decay products, right? So the W bosons, the Z bosons, the Higgs, etc., will be produced at very high momentum, which means that in the lab frame they'll be in this what we call this boosted regime, where the quarks coming out of them will be very, very collimated. So it's basically nicely illustrated here by this diagram, right? So this large radius jet that I mentioned before is what you need to fully encapsulate this decay product. And so generally what we need to do then is be able to identify these jets as coming from W or Z or Higgs boson decays and distinguish that and suppress the QCD background. So vaguely, well, broadly speaking, I'll call the techniques that we use for that the boosted boson tagging techniques, and I'll illustrate what they mean. So how do we do that? Okay, so here just showing a different illustration for W decay and a tracker and the colorimeters. So there's 3 ingredients basically that we need to do this. The first one is the mass. So, and the question what we're trying to answer is the jet mass compatible with the mass of a W or a Z or a Higgs? And so if we're correctly identifying one jet as the standard model boson, then the distribution of their mass should peak around their invariant masses, more or less, because there's some calibrations involved. So that's illustrated here for in blue for the W boson distribution. Background from QCD here is in red, so you see it goes to it has no intrinsic mass scale, it goes to lower mass scales here, pushed lower masses thanks to something that's crucial here, which is, and I mentioned before, that we can remove the contribution from pileup. Otherwise these masses would all go to higher scales. So that's one ingredient. Then the second one is what we call substructure. And it's basically looking inside the jet and determining based on the angular and energy correlations of the objects inside the jet, right? So the objects are composed from combinations of tracks and colorimeter deposits. If it looks, what we're trying to answer is, does it look like it has a 2-pronged structure, right? That is characteristic of a 2-body decay. So one example, and there are many ways to encode this information. So one example of a variable that we use often in Atlas and in CMS uses a variation of this. I think this is the D2 variable, where basically you see again in blue the W bosons sort of tend to have lower values of this variable, where the QCD background tends to higher values. And so higher values being more characteristic of a sort of more diffuse radiation jet characteristic of the QCD background. Then the third Ingredient then is flavor. This is relevant really mostly for the Higgs decay to two bottom quarks, which, as I said before, is the most common decay mode of the Higgs boson. So what's notable about B hadrons and what can take advantage of is that they are long-lived compared to the latter quarks, meaning that there is a measurable displaced secondary vertex in the detector. And so that's illustrated here in this diagram here in the top, where you get a jet from an original B hadron, and then it contains a secondary vertex indicating the decay. And so you can use information on the tracks, basically on the tracks associated to the jet in the detector, and combine that in what we call B-tagging algorithms for identifying jets that look like they came from B hadrons, right, and suppressing the light jets. And so, of course, for Higgs, you're looking for two B jets, right? So you're looking inside the large radius jet and saying and answering the question: can we identify two likely B jets inside? And if so, that looks like a Higgs decay. Okay, so we have all the ingredients for boosted boson tagging. So the next really crucial step, and I guess one of the main challenges in these analyses is how to estimate the background. So one thing to highlight is that it's very inefficient to generate QCD background from simulation with statistics that are large enough to populate this corner of phase space that we're selecting through all these cuts. So especially especially when you have so advanced boosted boson tagging techniques, right, that suppress the background very much. So the background in fully hadronic searches that I'll talk about is always data-driven. Sometimes we rely on simulation for some checks, but it's always data-driven. So it requires data-driven techniques, and I'll show a couple of different ones today. There's different ways to do this. There's no right way. So one crucial assumption here then is that the background is of course non-resonant in this phase space, and it's overwhelmingly QCD processes, and we'll have this smoothly falling distribution. And so the strategy for all of these searches is a bump hunt strategy, right? We basically scan the distribution of the diboson system mass and look for an evidence of a narrow resonant excess. Okay, so in this talk, I'll give three recent results in three different final states. VV, so vector boson, meaning WRZ search to a fully hadronic final state, a VH search, and a Higgs plus photon final state. So all of them illustrated here. Okay, so starting with this one, which is actually not the latest one. This is the one that's been around for longest, because it's I guess it's one of the important analysis to do as soon as you have more data, because it's a sort of a flagship analysis, and also it had a resonance back in, I think, in run 1. So that's gone now, but not a resonance, an excess, I meant, sorry. Okay, so starting with this fully hadronic VV final state, we get two vector bosons, each one of them decaying to a couple of quarks. So you have this two large radius jets in a final state that are shown here. So this is a very impressive event with an invariant mass of combined of 5 TeV. So we're looking for two large radius jets, right? Each one of them compatible with either a W or a Z, and we're using all the ingredients that I mentioned before. So the mass, this D2 variable, and also the number of tracks, which I'll get to. So the first one is pretty clear. So you have two mass windows centered around the nominal sort of values of the W and Z bosons. So you see here the mass windows, actually they go to they increase as a function of the transverse momentum of the large R jet, a large radius jet, and that's because these have been optimized by the signal significance that you expect. So you see here, basically at very high PT is where you expect much less background, so you can afford to widen those windows and let in more signal, basically. So something similar happens here for the D2 cut, which gets very broad at large PT, but at large transverse momentum, but again you prefer lower values, which indicate a jet that seems like it's a two-pronged jet. And then there's also the number of tracks, which okay, I did not mention this one before, but it's a useful variable when you expect So it's basically useful to distinguish between gluon versus quark-initiated jets. So this number of tracks will be higher for gluon-induced jets, which are the component of the background here, more than the quark-induced jets from the WDK, from the signal events. So that's both due to the distinct energy scales involved, as well as the different color factors for gluons and quarks. So you have these three sort of selections that you apply on each side of the event. Let's say we expect two back-to-back large radius jets. So now we can move on to the background estimation, which I would say is the trickiest part of any of these analyses. So it has to be data-driven, as I said before. So we have to have a solid strategy in place to estimate this background. One interesting thing that this analysis can do is so not just tackle the QCD background, which is the main one, but also actually use or select a control region in data that selects a bit of V plus jets, enough that you can sort of see this bump here from these V plus jets, then another process. And so by doing that, so this is a distribution of one of the jet masses in the event. Again, from a control region where the other side does not match a W or Z boson. And by doing this, you're selecting a real vector boson in data, and this allows us to compare how efficient is it that the combination of these three cuts is it in data compared to the simulation. And so from that, we can derive sort of a calibration of our efficiency, which is this scale factor here. This is applied later on then as a correction to our to the signal process simulation. But of course, the main background is always QCD, which is actually, it's shown here in the control region, smoothly falling fit here. And that's exactly how it is determined here. It's via this direct fit to the data in the signal region. So it's basically an empirical estimation with a bin maximum likelihood fit with this function that has these three parameters. So the way we know that it's a good description of the signal region background is because we won't unblind the region to check it, right? So what's done is that we tested in simulation and also in different control regions in data that are illustrated here. So B would be the signal region, and by inverting certain cuts, both event level and jet level, you can define different control regions in data, which are thought to have a similar composition, right, in terms of background. And so once this is confirmed to work, we can finally look at the signal regions and see how well our fit does. And so that's what's shown. So these are two different signal regions according to, basically you can combine them differently according to the signal interpretation that you're going to have. In the end, this is a WZ or WW signal region on the left and a ZZ or WW on the right. So if you see a few things here, first, this is very statistics limited, right? Just very high invariant masses from 1.3 up to 5 TeV in the invariant mass of the diboson system. So we run out of stats pretty much at 2.5, except for this 4.5 TeV data points. And the other things that the uncertainties, well, first of all, you can see the background description is pretty reasonable. The uncertainties are just related to the fit parameters, and there's no significant deviation here from in data from what we expect from the background nullity hypothesis. Okay, so from that analysis, we can go to the next one, where we can just change one of the particles in a final state. Instead of a vector boson, we have a Higgs, and now with the Higgs decays to a couple of B quarks. So we have a BB QQ final state. That's sort of illustrated here by, again, a different event display, but two large radius jets. This one with evidence of muons, so probably the Higgs candidate here. So the muons coming from the same leptonic decays of the B hadrons. So here I won't talk about the WZ side because it's very similar. I'll focus on the Higgs identification. So the most powerful handle that we have for identifying a Higgs boson decay is the two Bs, right? It's by B tagging the two jets inside a large radius jet. So it's something like what's illustrated here in this middle diagram. So you want to B tag these two jets. So the results that I'll show here are very recent from the summer conferences, and it benefits from an important change in the way that we perform Higgs tagging, which is illustrated by this diagram. Basically, we previously were defining these B jets inside of the Higgs candidate with some fixed radius that would at some point run out of acceptance. So you couldn't, as you go to higher and higher momentum, as it's shown in this plot, and that's the efficiency for that algorithm shown here in red, you basically can't really, so this y-axis is sort of a proxy for the efficiency of B tagging, more or less, more of a efficiency of finding two jets. And so basically at some point you can't resolve the two jets anymore. And that's why you have this drastic drop in efficiency here. And so one of the things that that was changed is that this algorithm evolved to a variable radius jet algorithm. So this VR stands for variable radius. And by doing that, you can recover dramatically the efficiency, as you can see here in blue. So you get a large acceptance gain at high transverse momentum. Okay, so all the other lines here, I'll mention one of the other algorithms later, but these are all three variations and big improvements with respect to what we were doing before in the previous results. Okay, so having said that, I'll now focus on the background estimation because it's very different from the direct fit approach that I just described for VV for the previous search. So here what's done is much less empirically based, I would say. It's more of an attempt to, so it's a density ratio estimation using machine learning techniques that we based on some a priori knowledge of what should change between the regions in data, right? About the kinematics involved, and I'll explain what I mean. And so first of all, we say, okay, so this diagram sort of illustrates the signal region, which is a region of events where the Higgs has a mass that's compatible with the Higgs mass, and these numbers are just illustrative. Actually, we changed these a bit, but what I want to highlight here is that it's in a Higgs mass window, and you found two B tags inside of the Higgs jet. So we can't use those events, right? And we don't want to blind the signal region to get a background estimate. So what we'll do is we'll extract our background template, our background estimate from this zero tag signal region. So it's in everything else, it's the same as our signal region data, except that it's events where we don't find two Bs. Okay, so we find zero Bs. So what we call the zero tag region. However, it's reasonable to expect that set of events in the background won't really describe the background in your signal region, right? That's fair enough. So there's just going to be different kinematics, and there's the B tagging efficiency involved. So what we do is we learn to differentiate basically the zero tag from the two tag using that sort of kinematic information. So the four vectors of the Higgs and the WZ bosons, and the four vectors of the jets, B jets inside of the Higgs. And so again, we can't unblind the signal region to do this, so we use the sideband. Because this is a sideband of basically a sideband in the mass axis of the Higgs candidate. So jets that are not compatible with the Higgs candidate mass. And so the useful insight here is that by training a BDT to distinguish these two sidebands, we can also extract basically a multidimensional ratio between these two regions. Okay, so weights that you can then use to reweight back the regions into agreement, let's say. And that's precisely what we do. So we extract a ratio here from the BDT classifier output, and the next step is to apply it to our zero tag template to try and get a background estimate for the two tag region. Okay, so that's the next step. Okay, so we apply this multidimensional ratio to the to the zero tag template. Of course, it makes an assumption that these weights that you derived in the sideband, that they translate okay to this through this x-axis, right, to the signal region. And so we don't just do this. We have to actually do something else, which before we even unblind the region, the signal region, which is make sure that, well, basically use validation regions in data to confirm that this is a reasonable expectation, right? So we look at validation regions that are not events in the sideband, not events in the signal region, just a completely orthogonal set of events, and we check that this 0 to 2 tag extrapolation or correction via BDT, that it does a good job. And I think well, there's a few plots in the paper. This is just 3 of them for different variables. This is the number of tracks in the Higgs candidate, the angular separation between the 2 jets inside the Higgs, and the transverse momentum of one of the subjets inside the Higgs. So before the BDT rating in red and after in blue with the data in the data points in the black ones. So we sort of conclude that yes, it does a good job, and of course we also associate some systematic uncertainties just to cover our bases. Okay, so having gone through all of that, we can finally have a what we want is to have a background prediction in the signal region, right? And specifically in the MJJ or MVH, or so I'll call it different names, but it's basically the invariant mass of the diboson system. Okay, so in this case, it's the MVH. So it's shown here in blue. These are specifically the ZH case. Okay, so this is for events where this is a Z and this is a Higgs, 2 tag and 1 tag. So just to say that, okay, so the 2 tag, first we run out of statistics, about 2.5 TeV in invariant mass. The 1 tag is still needed, actually, despite all those improvements in acceptance. B tagging at very high momentum is hard, so we lose efficiency there. So there's still cases where we can only find 1B inside the jet, and that's the plot here on the right. So you can see it goes to much higher masses in terms of statistics, and you can also see it has a lot more background. But yeah, so in the end, unfortunately, there's no evidence of an excess. So you can see it's pretty compatible, nothing really significant jumping up in the data. And so to finalize, I'll give a brief description of one of the very latest results. This, in terms of diboson final states, it was accepted just last week, this time for Higgs plus photon final states, which can occur, for example, in a sort of one loop decay, a vector boson, a new vector boson to throw one loop decay to a photon in a Higgs. But unfortunately, there's no event display for this search. So I found another one from a similar final state, not quite, I just wanted to have a photon in an event display here. So this is a Z to plus photon, and the Z goes to a pair of muons. So this is definitely not a jet, but this side of the event is a photon. So that would be similar. And actually it's relevant because this would be a complementary to this search in the sense that it reaches sort of lower regions that I won't cover here, lower mass regions. Okay, so this, I'll just have a couple of slides for this analysis. One thing to highlight is that, okay, so we have a Higgs plus a photon in the final state, a Higgs again to 2 Bs. And there's yet another method for identifying Higgs bosons that's used here. So it's one of those that I showed in the previous plot a few slides ago that was really recovering efficiency at very high PT, at very high momentum of the jets. And so this is what we call the center of mass method. I won't go into a lot of details. So just in a nutshell, what we do is we boost all the jet constituents, so the tracks and the calorimeter deposits, to the rest frame of the Higgs candidate. And that addresses one of the challenges in Higgs to BB tagging, which is we have to know how to assign the tracks correctly to each B candidate. So if you do it wrong, you lose information that would be discriminatory, that would tell you if that jet is likely coming from a B or from a light. And so it's very important to get the tracks assigned correctly. And that's what this method is trying to achieve here. You can basically, once you assign the tracks correctly, then you can, and you do it based on the assumption that you have in the center of mass energy, in the center of mass frame, you have back-to-back decays, right? So you can see using this method, the signal efficiency on the right, when you, after taking into account also the B tagging algorithm. So in red, the single B tagged and, the double B tagged, and the blue, the single B tagged. So again, you you do still run into the problem of low efficiency B tagging at very high masses. So the single B category is still useful at very high masses. So I'll jump straight to the results here. This is the data to background comparison. In this case, it's the diboson mass distributions, the MJ photon, the mass of the diboson system. And so the dominant background here is from gamma plus jets, or photon plus jets, and the strategy is similar to what the very first analysis that I showed. So there's a direct fit that's performed to the data in the signal region. So the function is shown here on the bottom of the slide, and it's obviously first tested in simulation and in control regions in data, sideband, zero tag. So there's a whole sort of validation to make sure that this parametric function is able to describe the background. So yeah, so you can see here the signal region with one B tag on the left and two B tags on the right. And again, no significant signs of deviations here. Okay, so of course we don't just check for deviations and that's it. When we don't find any deviations, we place upper limits on cross sections for potential signs of for potential new signals, and also provide exclusions, so max exclusions for specific benchmark signals. So the slide is just a flash. I don't want to go into details in each of these plots. It's just a lot of plots. It's just it's the results from the three analyses shown today, and also just to provide some context in terms of the masses that you see we're probing from several TeV. Actually, the Higgs plus gamma goes to a little bit lower than 1 TeV, thanks to the photon trigger, and the upper limits that are given in terms of sort of femtobarn sort of region. And okay, so I'm just including this here for completeness, because of course we need to put this into a wider context, which is then on this page. Because these are just three analyses of a really vast landscape of searches that, again, just to give an idea here. So this, okay, I won't go obviously through each plot in detail. I just want to say that basically these diboson searches appear, for example, and in this sort of extra dimensions and gauge boson search categories that you can then combine with the set of different final states. Also that many of the searches then can be combined with stronger limits and exclusions if we assume a particular physics scenario. So here on the top right, it's a combination of VV and VH searches. This is with just very the subset of the Run2 dataset, so this hasn't been redone yet, where in this very simplified scenario, you can put limits or constraints on the strength of the couplings of the new particle both to the Higgs and vector bosons and to the fermions of the initial state. And also here a particular map here on the bottom of exclusions in this HMSSM scenario, where a few of these analyses are dibosons, so in blue and in yellow. And again, this is actually not, it hasn't been updated yet with a full Run2 data set. So these all, just to say that these all obviously come together into a bigger picture, sometimes with some loss of independence, right, of model independence when you combine them. Okay, so the time that I have left, I wanted to talk about what comes next. So obviously, we have analyzed, for these three analyses that I showed, we have analyzed the full Run2 data set already, but that's not true for every analysis. This is still ongoing in many cases. But so in terms of the LHC timeline, the LHC experiments are of the planned upgrades in order to improve or maintain trigger rates as we prepare for the coming runs, which will have higher collision rates. And so if we put things in perspective in terms of the full LHC timeline, I think it's fair to say that with the data that we have now, which is about, let's say, it's not even 200 von Swettenbarn, we've collected, basically we're in early days, right? Because the HLLHC is aiming ultimately at about 4,000 inverse femtobarns.
Yeah, we seems to have lost.
Did you just lose me now, or?
Yeah.
Okay.
For a second.
All right. Okay, so I was just saying that.
Can you reshare your screen? Sorry.
Oh, yes, of course. Is it okay now?
Yes.
You see the same slide as before? Okay. All right. Okay, so okay, I was just saying that we're in early days in terms of the integrated luminosity that we'll be able to collect. But of course, that being true, it's also true that that's a bit down the line, right? So it will be a few years until we even double the current luminosity in the data set. And it's not like we're not going to get a significant increase in center of mass energy, unlike what we had going from run 1 to run 2. And so basically, it's a critical time to keep developing new analysis methods and ideas and make sure that we make the most out of the run 2 data set. So basically, the run 2 data set is going to stay with us for a while, right? And we need to mine it for new physics as well as we can. Oh, sorry. Can you see this slide change? Yes.
Yes.
Okay. So I just want to give a couple of examples of directions of developments that can improve the sensitivity to new physics with the current data set. And first one is, I would say, new techniques. I'll broadly categorize into new techniques. So I'll just flash three different things. And first one is jets. Obviously, jets play a role in all of the analysis that I showed today. And they need to be picked for particular physics signatures that we're interested in, that we want them to describe. And there's been a lot of work in improving jet reconstruction and specifically for boosted boson tagging. And so something that we already benefited from in the searches that I presented, in the first 2 searches that I presented, is these set of jets that we call TCCs, but I don't want to go into details there. Basically, simply put, there are jets where we can incorporate the tracking information into the jet substructure, right? So that gives us a better spatial resolution. We can benefit from the better resolution of the tracker, in addition to the energy resolution of the colorimeter. So that gives us, for example, in this D2 variable that we use to identify 2-prong jets, that gives us a huge improvement in the resolution of that variable, especially at very high momentum. So that gives us a lot of improvement in the performance of the taggers. But actually, this one in particular, these types of jets also lost in resolution of the mass, which we also use for boosted boson tagging. And so something that's coming up now, and it's not yet used in the analysis, but we're looking forward to, and it's in one of these papers here, or notes, public notes. It's this new unified flow objects, or UFO jets, that will basically provide an optimal performance across the full kinematic range that we're using, that we're interested in, from this sort of low PT region, relatively low, right? Low for these searches, up to the very high PT jets. So providing optimal resolution, both in terms of mass and jet substructure, which translates, then as you can see here on this plot, into improved background rejection. So going from what we had now, which is about, either in different analysis use different things, but either this star or this sort of red curve, to a little bit of improvement. So up to a factor 2 improvement, in fact, in background rejection, I believe. So that will obviously give us an advantage in reanalyzing data with better jets, basically. Then another possible shift in approach is related to how we identify the Higgs boson. By moving from we have very advanced techniques to identify the individual B jets that are inside that we expect to be inside the Higgs candidate jet. But we can move from that to an approach that is really optimized for the composite object that is the Higgs decay to 2B jet. So that means basically exploring the correlation, the flavor information correlation inside the Higgs candidate, right? So that's, put very simply, it just means training our usual neural networks that we train our individual B jets. We can train them on boosted Higgs to B jets and against the main expected backgrounds that come from thought processes and QCD processes. And so just to give you an idea, again, sort of a rock curve, as I showed before here, the QCD rejection in the y-axis and the Higgs efficiency in the x-axis. What we have now is this green curve, so we can, at least at very high efficiencies, have a very significant gain in terms of background rejection. So again, that better tagging techniques can give us a big improvement in sensitivity of how well we can target this this new physics final state. So something similar that can be set for another Higgs channel that I haven't mentioned so far, but I think we're running out of time, so I'll be very fast, is so also something similar to for the Higgs to BB is ongoing for Higgs to tau tau, where you also sort of move from this paradigm of identifying single taus to looking at the full large radius jet and identifying the specific Higgs to tau tau structure coming from there. So in this case, you can see here a big improvement in the acceptance as you go to this boosted strategy with respect to what we had before. But I'll move quickly along here. So just to be able to talk about the last topic here, which is the other direction that I think we can take that's related to broadening the scope of the searches. So the idea is that we, so far we're looking for new physics in diboson resonances, but what if we don't assume standard model bosons anymore? So what if there's some new bosons are also contributing to new signatures? And so there's a first exploration that was done with early run-through data in this XH final state. So now I sort of moved around. So there's a new Y particle and a new X particle, and this XH final state, basically it's a 2D search, right? It's a search in a 2D grid in the mass of the Y and the mass of the X. And actually CMS
It's just me, or we lost?
Yeah.
We lost, yes.
Yeah.
Same.
Sorry, we lost you again. We couldn't hear the last minute.
Okay, sorry, I think it's the problems of working from home, clearly. Okay. I think you should see my desktop now.
Yes.
The slides? Yes, okay. I don't know where you lost me, but I'll carry on from here. So I'll just say that I'll present a new search from Atlas that was made public this year, where we're searching for A to B C events. And A and B and C are all new particles, and no assumption on whether on either particle. Okay, so this is a perfect task for anomaly detection techniques. And I know that this is something that's actually some people here at LIP have been working on, and I know there's been a seminar about some related techniques not too long ago as well. So I'll just go straight to the next slide. So the analysis strategy is summarized here. So we have a generic search for a new resonance A that came to two bosons B and C. The only assumption that's made here is that A is a massive resonance, and that B and C are decaying hadronically into some like non-trivial jets that are also heavy and that can fit into a large radius jet. So it's something like illustrated here. And so the method employed here is this koala method, classification without labels. And the idea is that one trains a neural network in this simple classification task to distinguish between the signal regions and the sidebands, okay? So this being the diboson mass distribution. So you can see here sort of the parallel with the koala hunting that's made in the original paper that's cited here. And this method, basically what it does is it allows us to train directly on data without any need to rely on simulation either for the background or for the signal, right? And so completely model independent in that way. Okay, so I think this is just another diagram that illustrates the idea behind this. So we have similar to basically the supervised tagging techniques that I've been showing for W and X and Z tagging. The idea here is that you train a classifier that identifies the features that distinguish the signal region from the sideband. And you do that using the mass of the individual jets, the B's and the C's, okay? And let me just go back one slide because I just want to highlight here this diagram. The idea, the crucial thing here is that you expect, if you're looking into a signal region, they have you have two different populations, right, but are differently distributed. So you'll have more signal events in the signal region and more background events in the sideband. And that means that you're learning a proxy for what should differentiate between the background and the signal process. So once coming back to the slide now, this is before what I just said, before the selection of on your neural network input, but after you train it and after you apply a selection that you can define as something that, let's say you want to keep 1% of your background, or you want to keep 10% of your background, what you should achieve is that you should be enhancing the contribution of your signal if there is a signal there, okay? If not, you should just be randomly selecting background events. So something like this, right? So pre-neural network cut and post-neural network cut, you should highlight, you should enhance a bump. Okay, and so this page summarizes the results. So first of all, this search is performed in a huge range of diboson system mass, so from about 2.3 TeV up to 6.8 TeV in MJJ, and so it's split into 6 signal regions. Okay, so remember we need a sideband for each, which means that the sidebands for the first signal region and the sideband for the last aren't shown, so they're just outside of the range here of the plot. And for each signal region, we train a neural network that distinguishes it from the sidebands. Okay, so again, using the individual jet masses as inputs, as sort of features. And you can see on the top right here is an example of the output of such a neural network. In this case, for a particular signal region, so identified here with a star, it's this signal region here. And M1 and M2 are just the individual jet masses. So M1 is the heavier one. So this is the case here for pure data. So no signal is injected, and you'll see that by construction, you'll have efficiency regions with higher and lower efficiency. And then on the right, you see the same plot, but what if in the case that you injected some signal, some Monte Carlo, some known signal at 200. So you see here that you are sort of highlighting or here in regions of lower efficiency correspond to the signal-like regions, and that's what you're seeing here, something compatible with the 200 to 200 point. And so the next step is then to cut on this classifier, again, by selecting the lowest efficiency regions, which are the signal-like regions. And by doing that, you should be enhancing any localized resonance in the M1, M2, and MJJ space. And again, without any reliance on some model simulation. So this plot on the left-hand side is the result after ensuring a cut that gives you a 10% efficiency in the background. The background is parameterized with a fit function. You end up with something that is sort of discontinuous because they don't have to be continuous. So there's different neural networks trained for each region, right? So we're just showing the portion of the fit that's corresponding to each signal region here. And again, this is the model independent result. There's no evidence of any excess anywhere. But there's also a set of model dependent results where one trains the neural network with some simulated signal injected, and that allows us to also put some exclusions, some upper cross-section limits in specific regions of phase space, and interestingly to compare the coverage of this search to the searches that I showed before, where you have specifically 2 vector bosons or a vector boson and a Higgs. And so there's a few plots in the paper that show you how different sort of the phase spaces that we're covering with each analysis. So really, again, sort of a complementary sort of these complement the dedicated searches that I showed before. Okay, so I'm a bit late, so I'll just get to the summary. So I think I just want to say that I think there's clearly a great deal of things that are going on in the LHC, and hopefully that we can learn from the data set a lot of things that will help us understanding some of the questions answered by the standard model. What I showed today was just a subset of the many searches that are ongoing and part of a comprehensive search program in terms of final states and phase space regions that are covered. So these ones were the fully hadronic final states that are very performant at very high masses. But definitely we have a rich data set that we should continue mining for new physics if it exists, right? And if basically there's plenty of new ideas for how to make most of the data, both from designing better tagging techniques to just new complete novel ideas like this anomaly detection analysis that is broadening the scope and really targeting different corners of the phase space with minimal assumption of the new physics. And who knows, maybe that sort of thing will lead us to find something that is well, it's truly unexpected, right? So that would be great. So there's also a lot more going on that I couldn't fit in this talk, but I'll stop here. Thank you for your attention. Sorry for the internet breaks.
Thank you very much, Inês. So comments or questions for Inês? Yes, Patricia?
Thank you very much for the seminar. I did enjoy it very much. I have a question. When you presented this analysis QQBB final state, the background estimation technique is completely different and, let's say, more complicated than used in other analyses. Is there a reason why you need to go to this, or specific reasons?
So the reason originally was that we were afraid that because we're going through this sort of y-axis here of flavor, right? And the fear was that you were cutting into a region of phase space where the QCD background wasn't actually that well behaved. So we didn't want to hide some potential bumps by just doing a direct fit to the signal region. So the general agreement that we had back then was that, okay, the direct fit approach works pretty well for the VV, where you're just not dealing with any flavor information, but here, because this will have some non-trivial impact in the efficiency of the background, maybe we should do something more sophisticated. And actually, this is also used, it's not the only analysis that uses it. The Higgs, the di-Higgs to 4B analysis also uses a method, but they went a step further and used a neural network already. So I think it's something, and there's been a recent seminar at CERN also about these sort of methods. So it's something that I expect to see more often in the future, actually.
Okay, thank you.
Thank you. Elena?
Hello, Inês. Thank you for the seminar. So my question is very basic. In slide 17, so it seems to you that the deep wrong variable, it is quite basic, but how do you define it? Is the ratio of the PT of the jets?
I have a slide about it in the backup, but yeah, it's
so just you have also in 23.
54, yeah, so it's defined, so you have this endpoint energy correlation function, so 1, 2, and 3, basically that take into account the transition momentum of the jet constituents and their angular distributions, and then you make this sort of ratio, and this is why it's so impactful to have tracker information from the tracker, right? Because they go into this delta R distribution, this angular information.
So, and when you go to a very large masses, this tends to be, this PT tends to be unbalanced? Because you have, for instance, in slide 23, okay.
So you're asking me why we make it so broader, so much broader. In this case, so yeah, okay. This is maybe not the clearest thought. The reason this cut is so loose at high momentum is because this is optimized to maximize the signal significance. So this is just a reflection of the fact that there's not a lot of background there, so you basically can afford not to cut on that variable very much. So it's more a reflection of that. Although it's true that the resolution itself of that variable, I also have a plot for that, and sorry for moving around in the plots a lot. Yeah, so it does get a bit worse at higher PT, right? But still, again, with these jets in red that use tracking information, still it's a pretty good resolution, and it's a big improvement from what we had before, where we were losing a lot of information. So it was becoming much more broader and worse separation between the signal and background.
Okay, well, I have one more question, but please go ahead with other people because I have already one and I see many hands raised. If I have time at the end, I make another one.
Okay, thank you, Elena. Michele?
Yes, Inês, thanks for the nice seminar. I have a couple of questions. So regarding this full hadronic final states that you mentioned at the beginning, what are the triggers that are used or the thresholds for the jets? Do you know? Do you remember?
Yes. So both for let me just go here. Okay, these two use jet triggers, large radius jet triggers. The thresholds are pretty high. So at about, I think 400 and something GeV, I can't remember exactly, but that motivates us looking at so high, that's why we have to look at such high regions of mass, right? Because before that you're running into trigger threshold sort of problems. Yeah.
And then I have also another question regarding the efficiencies. So these targets that you mentioned, so you mentioned the W and the Z targets. I think it was slide 23 where you mentioned, I think I saw something 20–40%. And then towards the end, when you mentioned about these new methods, new techniques, or improved, let's say, techniques that what is the loss in efficiency in that, or at least if there is a loss in efficiency in using improved targets?
It's unfortunately, I don't think I can do off the top of my head a good comparison, because again, those numbers on that page 23, they're for that optimization specific for that analysis, for that background. So that's because before we were using sort of a flat efficiency, sort of 50 or 80%. That's what we were using, and I think that's 50%. That's why you have this star here. That used to be the baseline. But by construction,
so this 50% is let's say is related to the previous algorithm, the one that you had shown in slide 23, or at least in the first analysis you were showing.
No, so the previous analysis that I showed on page 23, that's the red one.
Okay.
But again, it's not a fixed efficiency cut. So we optimize the cut to be dependent on the PT so that we can maximize in terms of signal significance. So it's hard to compare, and we don't have the results yet with the new jets and with such an optimized tagger version. So that's not yet done.
Okay. Thank you very much.
Thank you.
Thank you. We have a question from João Gonçalves. João, can you do the question? Should I read? Okay. I actually see things going on in the chat. Maybe I will copy that to you later, Inês. So, Elena, do you want to do your other question?
Yeah, I'm curious about the improvement in slide 27 when you change your definition, substructure. So on the left you have, I think the constituents on the left are R equals 0.2 jets, right? And then you improve a lot when you allow to different radius. So one is 0.2, the other can be 0.4, right?
It's PT dependent, so it's not a fixed
yeah, I see.
radius.
Yes. The larger the PT, the higher the larger the jet. Yeah.
The crucial thing here is that it can go to smaller radii.
Even
so
small?
very, very small. Actually, the limit is very, very small. You can go to such a small radii that you can resolve the two B jets, right? That's the improvement here. Whereas before, at some point, you could only resolve one jet, and you can at most tag one B jet. Right. So it's I don't have on this slides information, but it's inversely proportional to the PT of the jet. This algorithm.
Okay.
Yeah. So it's more on this note actually has all that information.
Okay.
Does that answer your question?
Yes, I'm curious. In any case, I will see the notes. Thanks.
Thank you. We have one question from Nuno Leonardo.
Yes, hi. So if you could go to this, I mean, so you're describing this improved jet algorithms that are coming up. I mean, certainly there's been lots of developments in jet tagging and reconstruction in the last few years in structures. But here you mentioned these UFOs and TCCs and so on. Can you just tell us a little bit more? I mean, so what is this about? I mean, so you mentioned that you're using the tracking information, but I presume you do this by default, right? Is this something more that you could sort of, I mean, I know this is technical. I have no idea. We need to read the paper to understand the algorithm, but you could try to describe it.
So actually, we were not using tracker information for a long time. Say Atlas, right? I know CMS has bflow algorithms, but we were using these LC topo, right? Which is just calorimeter information. Of course, we then would match some track information to calculate some of the substructure and mass, but we are not building the jets with the combination of tracking and calorimeter constituents. So TCCs addressed that but they were really focused on boosted boson tagging. And so they did very well at high PTs, but they were not great at low PTs. And so UFO jets are basically a combination of the two strategies, of the pflow sort of strategy and the TCC strategy. They're sort of merged together into an optimal performance across the kinematic range. Yeah, I don't know if that addresses the question.
Right. Yeah. Yes. So thank you. Yeah. So you also found it an interesting acronym there for the UFOs. So that's cool. Now another interesting topic that is ongoing that you mentioned is this anomaly detection. So if I could ask about that as well. So very briefly, I think it's in, maybe if you could go to slide 47. So this is very exciting stuff. Well, I mean, so now I wanted to understand. So here you try to train the network, giving both the sidebands and the signal region from data. So this is model independent. You don't put Monte Carlo information or anything like that, as normally one would do. And so, that what your plot illustrates on the left, and you mentioned, is that the idea is to try to enhance the signal there. But my question now is, I mean. You're probably going to enhance the signal even if there is no signal there, if you are going to train using the signal region. Doesn't this happen?
So there's a few things that they do to prevent this. So I guess what you want to prevent is to learn the differences between sideband and signal region in the background, right? In the real background. So right. There's things like they do some decorrelation step to make sure that there's no information that identifies the MJD region that you're comparing based on the features on the individual jet masses. So I can't remember exactly the details, but there's a transformation that's applied on those variables, and then more importantly perhaps is there's a weighting down also of this. So you're using similar statistics, right, from the sideband and the signal region. I think actually I might have a diagram that exemplifies that. Not quite, sorry. Well, yeah, okay, this is what I have and it's not all that. So just when you combine, you sort of weight them down so that you're not drowning your signal region in sideband events, but I don't have any more information here. Yeah, so I think that should address the danger, I guess, of learning to differentiate the background of the signal region from the background and the sideband, right, which is what we don't want to do.
Okay, yeah. So you apply some tricks to avoid this, but because by default, indeed, I mean, I guess the network could learn about the formal momentum of the particles and distinguish based on the mass and then enhance the mass. But there's indeed ways of avoiding this. Okay.
But I guess so. This is a sort of this only takes the invariant mass of each jet, right? So this is taking limited information also of the jets. So we might wonder what happens if we use more information of the jets, like jet substructure in the 4 vectors of like the constituents or something. Yeah, but that hasn't been done here.
Thank you.
Thank you.
Okay, thank you very much. Any other urgent question? Okay, then it doesn't seem so. Then thank you again a lot, Inês, for very nice seminar. And yeah, if anyone is interested, I think you can send her an email since we are still in Malta. And yeah, thank you again. Thank you, everybody. And
Thank you, everyone.
talk to you soon.
Bye-bye.
Bye.